Oh, you can split. He will talk about first one and you about second.
I can also talk about second. No problem. First, then let us record this number. This set some definition here.
Mm-hmm.
And the P is P is this set. And we also need to know the CP. This is a formal series, but finite sum of formal series.
Yes.
Okay, so, and we want to prove that E, so I generate C, E. Yeah. First, we should see in SLN, the root system, actual root system in SLN will be J. This is the conclusion we already have, and we'll also have the for SLN we also have the restriction that yes, and so we just try to. Since this is the root, so this is our R. So we try to see what happens here with this restriction. Is this, but we know since this is the root of SLN, then we can see that this thing equal to 2.
Yes.
Yes. And then this is
it's easy to see, right? The yeah, so you have epsilon I plus epsilon j.
Yeah.
That's it. Yes, okay.
So then we have these should be some integer. So we can see that this is some integer equals I plus something depend on lambda. Definitely not an integer, but but it is.
Not depend on each I.
Right. We can see this.
So who is integer, who is not?
This is in, this is
Okay.
and then we have epsilon I, epsilon j also. This depends on I. This doesn't depend on I. And this just depends on lambda. And we have this. Right. And if we plug in epsilon j, and this will be a ij. If we minus this 2, this is what I minus ij, and this cancels out.
I agree, yes.
And well, we use this thing. And it just means this is 0, so this whole thing is 0. And this n doesn't depend anywhere. This n is just a little SL. Okay? And well means n is some integer over n. Right.
Some integer depend on lambda.
Why integer?
Because
these are all
this
integer.
is 0.
This
Yes.
and this. So your R lambda will be this. Right? But this is the thing we
That is, the next part is what I didn't believe.
Okay, so you prepared us that you're going to lie to us now, right? Maybe not. We need to check.
Okay.
Wash the hands. Okay.
Oh, see, so since P is a group, right? With
C of P, P is group, yes. It's an abelian group.
abelian group with this one, right?
Yes.
But I will say that this is isomorphic to this. We just time and upstraight n.
Groups and
Sure. Yes.
And then it means that if you put your let me see. Yes, here your R lambda is n over some lambda.
So if we're talking groups, then it's just d to the n, right?
Ah, yeah.
To the whatever, to
Yeah.
r.
And you just time n both sides, you will get something called n lambda become y. And this is integer. Right?
So n lambda epsilon I
Yeah.
is
Integer.
integer.
Of course. This is integer and this things above just this.
So
minus this.
sorry, can you repeat please the part about where this dots? Why is it an integer?
So this is 0. So n times r lambda equals minus I1 minus in, right? But these for all of them are integer. That's our assumption. And so our r lambda is this one. And this is method.
Yeah, some integer depend on lambda. Yeah. No problem here. But I don't know why this can help.
That is kind of bothers me a little bit because
You mean this part?
yes. So we have a representation like that. I think if we take just not that, so the difference, so it's I think we can take any even complex entries for lambda for r of lambda, because r of lambda is what from the general theory, it's how the center acts, right? You can shift it to whatever you like on any complex number. So that's why it bothers me that you got that r lambda is actually a rational number with actually some concrete denominator.
But with a restriction, this is actually integer.
Yes.
Oh, I see. I see what.
I mean, you can. But yeah, I don't see right away a mistake. But I know that you can. So the whole idea is that, so you quotient, right, by this relation. Remember in the second part.
Yeah.
So this relation actually means that you can shift your lambda to anything, to anywhere.
Yes.
And this R of lambda is actually this simultaneous shift. And it's not fixed. I don't know how. Yes, I don't know.
So, but
Yeah, but this.
yeah.
Where is the mistake? That's another question. Which is a harder question. But the thing is, you don't need all this, right? So okay, your reasoning after that will be that this is an integer, right?
Yes. And then we can have some combination to get some n number here.
Mm-hmm.
This means we have some times we do g, then something we will get this.
Okay, but still, I think something I cannot say right away what's. Yeah. So what's but let me just say that this set so P is also direct sum of z times fundamental weights, and fundamental weights are defined as follows: omega I, alpha j, alpha j, alpha j, and then 2 here is delta ij. In our case, this is also 2, right? So actually we can erase this. And then alpha j, you know what they are, right? So you need omega I, e, so epsilon j minus epsilon j plus 1. So with only simple rules. We just need simple rules, right? Is delta ij. So then who are omegas? So it's easier to visualize it using just, so your root, in your root you have 1 minus 1 at some place, right? And you need some other vector such that their scalar product is 1, but with everything else is 0. So if your alpha is like that, then omega I should be like that. You take all the ones, and at this point you take 1 and then 0. So this is your omega I. Because when you compute scalar product, it's just alpha I gives you difference between this one and this one, right? So it will be 0, 0, 0, then 1 minus 0, and again, right? So if you take some alpha j, alpha j, it will give you difference between 1 and 1, 0, or between 0 and 0. So the only difference that matters is this one, 1 and 0. It gives you delta ij. So your fundamental weights are like that. Now the question is, can you obtain epsilon I as an integer linear combination of omega i's? Right? Then epsilon I is another basis in P, right? So omega is a basis in P. If you can obtain epsilon I, right? Of course, you can obtain omega out of epsilon I, right? But can you obtain epsilon I out of omega, just linear combination of omega with integer coefficients? So you can, of course, right? Because, for example, what it is? It is omega I minus omega I minus 1, right? So integer coefficients. So this is another basis for P. Since this was basis, this is another basis. And so therefore e to the epsilon I degenerate. Yeah. Okay. So then part 2. And the only relation is the one that Oshi just erases. Epsilon 1 plus epsilon 2 is plus epsilon n is 0, and that's exactly the relation we quotient by in P, right? So it's well-defined homomorphism.
Okay, so first I need the general formula is the character of some first weak representation is his Weyl scope and the length of this element.
Mm-hmm.
This is it called shift action.
Mm-hmm.
Yeah, and I need to calculate the specific form for what? For SL1. Yeah, so G is SL1 and lambda is just some random lambda.
Mm-hmm.
So I just take everything inside here, and we know something about the Weyl scope of this algebra is from some other seminar we got this. And length of
Moreover, we know how it acts on lambda i's.
it's
So not only isomorphic to this, but it actually permutes exactly this lambda i's.
so this
Yes.
action is if this W is a simple reflection, then this action is some that name just change two elements.
Yeah.
It's quite
Two cycle, I don't know.
two cycle, yeah.
Yeah.
So that means this. Actually, I want to see this. This is a sign of if we treat this also like element in here.
Mm-hmm.
Yeah, it's like this. So okay, and yeah, that's all, and we just
Yeah, so L of W is a parity of corresponding
it's
permutation,
correct.
right?
So we just use this information, and we get the formula required. Okay, we start to rewrite everything. This side is so this one becomes the permutation group. So just change the notation. Sigma from Sn.
Mm-hmm.
Sigma is just that's a sign.
Mm-hmm.
And this E of that, it becomes we also need this. This means we so this P. Where is already P? So I denote
So P beautiful, yeah, I don't know. Different P, of course.
this P.
Yes.
This P is so this I, yeah.
Mhm.
Mm,
Can you write a formula of what is, just to recall, what is W dot lambda?
that is W act on lambda plus rho minus.
Yes.
But yeah.
So
but
the question is,
we
what
will
is
have-
rho?
Rho is what is rho? Rho is the sum of
It's half sum of positive roots,
positive root, yeah.
but
But we don't actually need this. So just need how it looks like in S and P.
yes, that was my question actually, yes. So what is rho in our particular case, S11?
So this guy becomes in this beautiful P, which will be like this guy. This symbol becomes
Yes. I mean, you have epsilon I, epsilon G, and
yeah.
if you write rho,
We have some lambda is something like lambda I epsilon I. Yeah, we have some decomposition, so this guy becomes
Mm-hmm.
xi
Yeah.
with lambda I and
Uh-huh.
this guy becomes this. So so here we have this element act. I with the action lambda sigma I. Yes, this is the scene.
But this is not, I don't know what, but this is
Here.
this is not true.
Here is also.
no, the power is not.
The exponential, it's not, it's a dotted action which you just wrote, right?
Yeah.
But you wrote just usual action.
Yeah, but after we change everything to yeah, we just change everything to the coordinate and this
Yes.
becomes
No. Permutation of lambdas correspond to usual action.
I mean
I think you first should write rho.
this is the permutation.
What I'm saying is the following. So this is okay. So what I'm saying is that what is sigma acting on lambda? It's just well, lambda sigma. Maybe, by the way, sigma inverse here. I don't know.
Yes,
So always.
yes.
I forget how I did this.
Like this, right?
Yeah.
But then you need not sigma, but sigma dot lambda, which is related to sigma of lambda by this. So the question is, what is rho in SLM?
Yeah.
Forget this.
Rho is just I less G epsilon I minus epsilon G power G. And you should count.
Yes, you
count
should.
the number. And I don't know how to count. I'm not good at counting. But I can tell you the count. The final answer will be.
I did this part, but
N minus 2I plus 1 epsilon I. Yeah, maybe you should explain how to.
yeah, this is.
You have a question?
Said you should explain some factors.
Yeah, I know.
Yeah,
This
sorry.
is just we take some, but the index is not that well. So there is something with minus, something with plus. So how many? If we just say fix some I and we see how many minus thing, how many positives, how many
Yeah.
Yeah, how many things from here, how many things from here. It's just if we fix I and we look at here and if this one is
Just fix the first one.
yeah, and,
Yes, you should say.
yeah, and how many epsilon I will appear here is depending on how many G we can choose here. And
Yes,
G,
which
the
is
condition
great.
for G is it should be bigger than I. And how many things will be bigger than I is I plus 1 more 2, maybe n or something. This should be just n. So, yes, because here. So the number here is n minus I. Minus I is the number of positive epsilon I. And if I is appear here, then we get something minus. So how many epsilon I will appear here? It's just the freedom number of how many this. So it can be only 1, 2, 3, minus 1. So we have minus 1 minus thing.
Yes. So
This
n
one
minus.
minus this one is got this.
Yes.
So all we all agree with this one.
Yeah.
Yes.
We agree with this.
So actually it is n minus 1 1/2, n minus 3, n minus 5, and so on. And the last one is negative n plus 1, right? So this is raw.
So this is the coordinate of rho, and
I think we should keep this. Since this is and we will say is in Rn, I mean had ni. This part is the coordinate. It's ith coordinate, right? And when we add these two vectors, the ith coordinate of this is lambda I, and plus this ith coordinate, and you then take a sigma x from there, and the minus the ith coordinate. Then you will get the ith component of these things. And you plug in there.
Yes, the coordinate of this guy is.
Let me simplify you the life. Let me say that actually you can take, instead of this row, you can take this row, n minus 1, n minus 2, and so on, all the way up to 0. So up to shift, they are the same. So you shift in this way that this here is 0. No. Like simultaneous shift. Not this one, but simultaneous shift. So every vector that appears, every weight that appears, you have a freedom to change once you just subtract or add the same number to each of the entries. Because of this relation that you quotient by x1, x2, xn minus 1. You quotient by it. So every weight that you put in exponential, you can change by adding the same thing in here. No, not multiplying without 1/2 here. You see? So I claim if you add n minus 1/2 to this, to each entry, you will get this.
I still want to do this.
Okay, if you wish, because this is exactly. So remember, in Char polynomial, you had x to the lambda j minus lambda I plus n minus I. This n minus I is exactly ith entry of this row. So that's why I wanted. And then you have lambda j. No, okay, you can continue.
Okay, I just write this term in coordinates, it means I will erase this part.
Mhm.
But now it's
Okay.
just some trick. So in the ice, it becomes
You could just this times this.
Yes.
lambda I, but it's not I because we act on that
Oh.
thing, so it becomes this. Plus this thing.
Yes.
This thing is plus 1/2 of n minus sigma I plus 1. And
Plus 1/2.
yeah, plus 1/2. And the last thing is without change the without change the sign.
Uh-huh. So it should subtract.
You should subtract this.
Yes.
Yeah.
Minus 1/2
part
plus
plus
I.
Minus 1/2. Yeah.
Yes. Something cancels. Mm-hmm.
It would be I here. Yeah, so
Mm-hmm.
it's this will becomes the x's power, I think, right? No, that i's power. Or sigma I.
Yes, it's w dot lambda I. That's exactly what you wrote here.
Yeah.
Yeah.
This
This is exactly.
Yes, it becomes I. And also here, this should be the positive root, but positive root is very simple.
Yes, of this sort.
Like this.
Yes.
So it's, I. 1 minus positive root,
x3 divide xi.
x.
J x3.
Yeah, xj divided by xi.
Yeah.
Uh-huh.
So because of in the shortest polynomial we have a Feynman, the Feynman.
Goddermont, yes, okay.
Feynman determines
Mhm.
this side. So, but that this looks same, but we need to
Multiply by
something
some.
here. Yeah. So we just do it next step. Not like this thing. This time just simultaneously multiply this guy here and it will
Mm-hmm.
appear here.
Mm-hmm.
Minus xg. Okay, so what is the thing I should multiply here? I just
Xi, product over xi. Right.
yes, yes.
Product of xi's over I less than j, right?
There is maybe some coefficient. I need to count something again. Yeah, but here it is still
The same?
this same thing.
Yeah, okay, just not, just, yes, okay.
Let's
And,
remind you with the formula.
We
We
wrote
wrote
formula
yesterday.
here. What is
This is k, and this is xk, n minus k. Oh, that's it.
explain
Mhm.
minus k. We have a minus k here is because how many xi here I should multiply here.
Mm-hmm.
We should count it and yeah, and we just
So how many j's bigger than I?
yeah we just consider
N-
how
n
many
minus
j
I,
bigger
yes.
than bigger than I, then this is
Yes.
that minus.
And notice that this factor is exactly x to the power rho.
And you already count here. It's n minus I. Minus I. Well,
Yeah, and yeah,
Just
we can
advance.
just change this to I
Yes.
and times this thing to this side,
Yes.
and then we
exactly.
That's
Yeah,
exactly
now
what
get
we would
the-
like to do.
Yeah, the answer.
Okay. Thanks. Okay. Thank you very much. Then okay, so Christina have some idea.
Okay, we have a homomorphism. I wrote from group CP to C equals -1. And when we apply our map to review, will become Q in power 2. Okay, and the first step we need to show that okay, and everything here is for alpha minus Q minus lambda. Okay. Yeah, our Q, as I could understand here, is just a complex number.
Or a variable. Doesn't really matter.
Okay. Okay. Yeah, so I just used, first I used Weyl character formulas to write that, I hope I realized it that correctly.
No, it's already there.
Yeah.
Okay, very fortunate. Okay.
Yeah, I didn't erase that. Yeah, and so then we just need to apply our homomorphism. Okay, so actually my formula was a little. Yeah, but it's the same. Yeah, I just wrote here.
So you would like to rewrite it somehow, right?
Yeah, it was like this, V lambda. But maybe because of that I also didn't get the right.
No.
Oops, yeah. Sorry.
So no dot and like this, right?
So our homomorphism will affect this part, and with this I actually don't know what to do.
So look, Christina. So on the right hand side you have also some fraction, right? And in both numerator and denominator you have kind of symmetric situation, right? Your exponential is actually like, okay, look at denominator, right?
Okay.
The denominator is the first step, right?
Yeah.
So here in your denominator you have kind of the same looking terms, but one is with minus an exponential, right? So kind of symmetry with respect to taking inverse with in q to the one power and q to another power, right? And how we can make this symmetry here? So it's now 1 minus something, right?
Yeah, but when
So we would like something e to some power minus e to a negative of that
yeah,
power,
but with
right?
this, I think it was pretty simple. No, maybe I'm wrong. Like because when I apply homomorphism to this part,
Yes.
to numerator, yeah, it will be. Wait.
Yes.
Like
Why if you apply?
Um,
What?
also, it was written here in mine that was like second. Here, why is here?
No, everything is correct so far in this
Yeah?
form. Yes. You can of course rewrite it somehow.
Yes.
Okay. Okay, in my actual notes it was like this. Oops. Yeah. E alpha.
Excuse me.
No, it should be one here. Okay.
Yeah. Okay. So
But
you
minus-
can you give a hint to Christina?
Okay. So and remember in physics several times we do like you can write e to the power minus alpha as minus alpha by 2 and alpha by 2.
Yeah. So you need to rewrite this somehow, right?
Write
Yeah.
alpha as
Yeah.
a sum of alpha by 2 plus alpha by 2. E to the power minus alpha. Right?
I cannot remember what you said.
Okay, I'll just say things
Yeah,
from
it's
you.
Okay.
So you can write just alpha as sum of alpha by 2 plus alpha by 2.
Right. Just
Just
two equal pieces, right?
Just divide alpha to 2.
plus
times.
alpha by 2.
Can you write?
Okay, so maybe let's send you to do this. Yeah. All right.
So I was saying
Uh-huh.
just this can be alpha by 2 plus alpha by 2. Okay?
Yes.
And then it becomes 1 minus.
Right.
Then let's take. So this is 1 minus e to the power minus alpha by 2. And this is, you see, it's of this form.
Yes.
Okay, with this here it's simple because when we apply it will be one second, I need to again remind myself what was that. Like because rho is 1/2,
Mm-hmm.
yeah, so of all
Yeah. Yeah. It is here.
yeah, all positive roots.
Mm-hmm.
So yeah, that's 1/2
Yes, exactly. And there is a product
will
also.
disappear. Yeah, so it will be just okay. Yeah, this part. Yeah, so we will get here this.
But you see, it's exponential to the
Yeah,
power.
but also should this should go like
Outside because the product for alpha is just sum e to the power.
Okay, yeah. Okay, so it will be.
So I suggest, okay, your denominator is already there.
Yeah.
Okay, so write it down. But what's left? So you have this expression over product over all these things, right?
It will be a Q, lambda, yeah, and but no, this and here.
Mm-hmm.
Okay, and here it will be
Sum.
still sum. Okay, and okay, after it will change, after applying homomorphism. Yeah, and this it will be, can I write like this? At least now it will be rho minus rho. Like this. Can I leave it like this?
Mm-hmm.
Okay, now we need to think what to do.
That's not all, right?
Yeah, I'm still.
In the denominator, also you have e to the power minus.
Yeah, you have p or p beautiful of product of e over alpha 2 over alpha in R plus. That's what left, right? So you have all this stuff you factored. This becomes denominator. This is left.
Yeah, but I thought
But-
I here.
Uh,
Cannot do that.
but where do you have lambda then? This does not depend on lambda. So this is okay. Then yes, you're right. Then let me erase this. I didn't realize that this thing is your. Then it's 2 rho 2, like that. It's exactly something that you need to cancel this minus.
Okay, yeah. Okay.
Mm-hmm.
Okay, so this second again, yeah. Q. Yeah. So it will
Mm-hmm.
cancel. So the rest thing is sum. Minus 1 omega. Okay, and what by that?
No, it's inner.
Hmm?
It's an inner product of it. No, that's it. It's not just a double x.
Oops.
Okay. Yeah, we can just ignore it. Probably.
Yeah, and
So now the question why it was written in numerator, so it's written numerator there, right?
yeah, actually, for that I found some formula that was called Weyl dimension formula.
Well, denominator formula.
Denominator, yeah, okay.
Yes.
Yeah, so and I just applied that, but I'm not sure that.
No, that's the whole point. Why? So this is the
Yeah.
only representation theoretical thing that
Yeah,
is
but,
needed here, right?
in
So
our case,
maybe somebody else can continue,
I
right?
also didn't make much progress. I was a bit stuck
It's
at
because
this point.
the W
I
will keep
can-
the invariant.
I can take
the
care
inner
of
product.
the. Okay, I will tell what. I
Okay.
do.
Okay.
Okay.
Yeah. Thank you.
So this is right now equal to character. Wait, let me see the formula. Sorry, just a minute. Dimension. Wait. Yeah. Wait, what are we doing here right now?
It's not dimensions yet, right?
It's character
Uh-huh.
and
Uh-huh.
Okay.
Well,
It's
p of that, right? Well, it's good, but it's pi rho. Sorry. Yeah, pi rho of character of lambda. You're doing everything good? Yes. Uh-huh. Mm-hmm.
So, okay.
Mm-hmm.
So in the final expression that you had, this one, there is no this term.
Mm-hmm.
Okay, so we can try to get rid of that. For that, okay, I didn't write it yet this. I can just write this term as of now as just what we had, which is exponential e to the power dot lambda, which is lambda minus rho.
What? No.
I mean, I'm just doing this because I want to get rid of this term first.
No.
So I can take lambda to be 0.
So we are working with this numerator. We don't apply pi rho yet. Okay, so let's rewrite it in this form.
So
Yeah.
you should not apply.
Yeah, okay. Basically, the idea is that let's just go back to what we had, which was
Yes.
and here was to the power, I think it was minus 1, right? Okay, and now I can take lambda, yeah, so I can take lambda to be 0. I just want to check what happens then, and this becomes, I think it's w lambda plus rho minus rho, okay, and okay, character, and then when we have lambda to be 0, L lambda is just the trivial representation, which is just C, and character of C in general is sum over mu, dimension mu, e to the power, I think it was minus mu or plus mu, I don't remember.
Just mu.
Just
right.
mu, okay, yeah. This is what we had, okay, and now we are only considering this case, so mu is just 0, no, just 1, sorry, and e to the, wait.
E to the mu is 0
Mu
and
is
e to the 0 is 1.
Dimension is 1.
Yes.
So dimension is 1 and e to the power 0 is 1. So you just get 1.
Yes, on the left hand side, just from representation theory, we get 1, right?
So we have 1 here, which is equal to, and this is exponential of w, and lambda is 0, so we have just minus rho.
Yeah.
Um,
So you can cancel e to the negative
yes,
rho.
Yes, this can be just cancelled. And here, I didn't write the full term here. And this is,
Yes.
is equal to this thing.
Yes.
Okay, so I can again just go back to my, wait, I will write what was, yeah. So we had w in w minus 1 to the power n of w, and again it is dot, it is w lambda plus rho minus rho, and here I had e to the power minus rho, and this term is equal to, again, sum over w and w minus 1 to the power n of w, and just one more term, I think e to the power minus rho, is it? With sum, yeah, and this term will go away. Is it okay? I see. Or am I making some mistake around here?
Which term? Which one did you erase?
This e to the power minus rho outside, and here we had a rho.
Ah, okay, yeah.
Okay, and this.
But maybe here you have the. So on this side you have w of rho, then.
Yes, yes.
And this one cancels. Sure.
Okay. But because we want at the end this term here.
So maybe let me help you out
Okay.
here. So you already got the hard part, the Weyl denominator formula that Christina found. So the main idea is to say, okay, for character of trivial representation is 1, right? Therefore, what is in numerator equals to what is in denominator, and that's exactly Weyl denominator formula. Okay, but then you can take not pi rho, right? So pi rho was what? You can instead of rho you can take any weight. You can take pi of rho plus lambda, for example.
Oh, yes, yes.
And
yes,
apply
now I
it to
remember.
here.
Okay, so this is, as of now, it is pi of, rho, was it rho, and let me just check.
So I shall suggest to take pi rho of lambda that takes e to the mu, right, and sends it to, so pi rho of lambda takes e to the mu and sends it to q to mu rho plus lambda. So just apply it to both sides of this Weyl denominator formula. Yes, I think this is the one, yes.
Okay, let's see.
And you will get that the numerator of what we got is exactly what's written here. The only thing that is needed, it's a lot of written, is that this equals to this.
Yes.
That's the only thing that we are missing. So I say that it's this missing part is exactly applying p rho plus lambda to this equality.
Okay, let me see.
Because denominators we checked, numerators is just applying p rho plus lambda to this, to the Weyl denominator formula.
So e to the power alpha by 2. You are saying I apply on the whole part
Yes.
pi of lambda plus rho. I think, right?
Yes.
Okay, and rho and e to the power alpha will become e. Okay, we had alpha by 2, so it will become alpha, comma, lambda plus rho minus e to the power minus of alpha, comma, lambda plus rho.
Yes, exactly what's written here. It's the left hand side.
Okay,
The right hand side
is
is exactly what's written here actually.
so minus rho. And we have w rho. So it is twice this time, twice of
Yeah, but without not e only but q.
oh yeah, no, this is q.
Yes.
This is q. This is q.
This is exactly what you would like to see, that this equals to this. This is exactly what's written for there.
Let me check. Oh yes, because again we have a 2 term here. We can
Yes.
just write this. Okay.
All right, so
Okay.
you're done.
Okay, now the second part.
The second, yeah. So if somebody else would like to do second part, just to let us.
Yeah.
You can. I see.
Maybe someone else can.
So nobody volunteers, then you sure you can do.
So finally we have the formula, which is, let me write it down, which is and this map that we had is pi rho, which takes us, okay, wait, and dimension of L lambda is summing over mu, dimension of mu, e to the power mu.
Without e to the power mu, right?
Oh yes, now we say that we take it to 1.
Yes.
So that then we can get this,
Yes.
right? And so we can take q to 1
Yes.
here because q is the exact mapping of e to the power, okay?
Mhm.
So when we do that, essentially we have something like 1 to the power something minus 1 to the power something, so we are just getting this, so it's a 0 by 0, so we can apply the, take the derivative on numerator and denominator simultaneously.
No, it's
And
called what? L'Hopital's rule.
Yes.
Okay.
So we get lambda plus rho, comma, alpha. Again, we will have it 1 to the power something, but that's okay, 1. Minus, plus, yeah, lambda plus rho, alpha. And again, the same thing, 1 comma alpha plus rho comma alpha. So it's just lambda plus rho comma alpha. And rho comma alpha.
Yes. I think. Was it?
I think that's what we have.
Something. So if you take derivative, the q is still there, but what's important is that you have lambda plus rho times alpha
Yes.
times q to this power plus q to this power.
Yes. Yes,
And then it's already, you can put q equals 1, it's not 0 then here, right? It will be 1 and over 1, not 0 over 0, because you have plus here and plus here, actually. Yes. So in this formula, something is, I think it's this times this plus this over this plus this. This should be correct formula. Okay. Thank you very much. I'm very curious how people did number 4. Actually, Ebner, did you do? Freudenthal formula. So you claim that you do, right? So.
But
Okay.
it's really long.
So maybe a main idea.
Yeah, it's like to calculate the traces with of the representation of the.
Maybe you can, write something.
Of the
Yeah.
Casimir elements.
Yeah.
That gives you the dimension because they act as just multiplied by scalar. In the models of height weight, like here they compute how it looks the trace in that space.
So first of all, can you write the formula? So what we're trying to prove?
Yeah, we want like it was like C lambda minus C mu. The dimension of lambda mu. Yeah, it's right.
Well, it's dimension. Yes, it's just m lambda mu is dimension of L lambda mu.
It's 14.
Okay, so how do you approach this?
It was.
So knowing the multiplicities of all higher weights, right, which is finite number, right, in Verma model, for example, you can find a multiplicity of your given weight, right? So that's what this formula. And sometimes this one is in practice is better, like for big, well, just than the Weyl's character formula. because sometimes W, like the Weyl group, can be very huge. Just to compute something explicitly is harder.
They first use like CL, lambda for example. And
So
they
C
write-
lambda here is the eigenvalue of Casimir operator.
This can be C, but this is like the Casimir operator like directly, and it's this is in the algebra, the universal algebra, and we will write it as first the section of the Cartan algebra, and then in the other like models. This is the dimension of Cartan. On this root system. No, this is like in general. Or it should be, for the Casimir it should be.
Yes. If you need to specify what it is, but I think this one does not depend on lambda. It's just Casimir.
Yeah.
And C mu, for example, it's so actually like a Casimir acting on M mu is identity times C mu. So it's the eigenvalue of C in the Fermat model of highest weight.
The last problem is that we already have also
Yes.
this element in this.
Yes.
So, and then,
But this formula we also need.
so according to this, they calculate the trace. Actually the trace is that. It's like
So trace of what? So you calculate
trace
what?
of in V mu. Can be they use like the model in mu of high weight mu, and they say like this looks like this, and already the representation. And it's like just the C plus the dimension of your.
What is V mu? Let us be more specific.
Mu is the module of highest weight mu.
This is not really what you would like to. It is no. Why is this then true?
Did we study this general form of Casimir?
Yeah, actually, it's really long. So
Yeah, but this one is easy part.
because this acts just like multiplication by scalars. So it's like after we have the trace, we got just the dimension of this.
But this is dimension of what?
Of this one.
But this is what?
This is the. We have V. It's just the module of G module, for example.
Yes.
And we take just the V mu because these are the same as direct sum. This V mu.
So this is called weight subspaces.
Yeah.
Right. So this is not a representation of highest weight mu. It's a weight subspace inside Fermat module. Moreover, not maybe Fermat, but in our case it's a finite dimensional reducible of highest weight lambda, right? So actually, what stays in here, it's actually should be written like this: L in our notation, L lambda and weight mu.
Yeah.
So Casimir operator, of course it acts by multiplication by number. So it can be restricted to a subspace, to any actual subspace of L lambda, but we need this one. So it's diagonal in this subspace, right? What is this matrix? This matrix is like that. It's C lambda. We know that it acts by C lambda in L lambda. So actually my row of C lambda restricted to L lambda mu is this thing. Because every vector in the base is just multiplied by C lambda, right?
I had another question.
Uh-huh.
Just that I don't remember, maybe I missed a couple of lectures in between. How is I just remember it as xi, and then.
Yeah, so this is the same, it's just Abner divided it into sum over basis, some basis in Cartan subalgebra, and sum over root vectors. And so these are dual to the root vectors.
Oh, okay.
So Z is the dual to X alpha respect to with respect to killing form. And Ki is dual to Hi with respect to also killing form, yes. But if you compute trace of this, it's what? It is C lambda how many times? So a dimension of V lambda mu. So exactly the size of this matrix. So it's M lambda mu. So this is an easy part. On the other hand, you can take this particular formula, right? And see what is the trace of this in this subspace, right? And how we do this? Yeah.
We do it by parts. Like first,
Yes. So far, what?
We have only done the trace of the Casimir operator.
Yes, but we need to compute it in two ways. First, knowing that Casimir x by this number is this. It's only this part of this formula.
Yes.
And the other way, using this formula, right? So we're actually computing trace of this in this representation, plus trace of this in this representation, and so on. And this will be everything else, including C mu times M lambda mu.
Okay, so first they argument that the representation how acts Hi and Hi is by scalar. It's just multiplication by scalar in this lambda lambda mu. Here this is like the representation of Hi. Also they act as multiplication by mu Hi in right? So
Yes.
also for that's Ki. Okay, so they takes mu in H rectangular algebra such that mu H it's just the given form of this vector and H for all H in Q. And we rewrite it this as again as an element here. Well, actually in cartons. Okay, and so we have that when we evaluate mu in this Hi. It's just definition. Of the clean form
Just linearity, I guess. And yes, and from. So what I guess we're trying to do now is to compute that trace of sum Hi Ki over L lambda mu is M lambda mu times m mu mu.
Yeah.
So if you take this element and act on any vector, actually, in emblem the mu, you will get just a square of mu. That's what we are doing, right? Mm-hmm.
Yeah, and after that, we get that combining. We have
No, but let's check.
Ah.
So
Okay.
where is this?
Okay. Yeah, so we have this, and we have that the form of mu by duality.
Mm-hmm.
Same as I and J. Of the given form of Hj,
Mm-hmm.
acting by just scalars. Yeah, and from here we got that. Because this. Yeah, I think this is.
From here to here is not clear. How do we get?
Yes, because the paper is that from here.
Okay. How on the left you don't have k at all. From like the second equality. How do we get? So this one, right? This one, also not so clear though. So can you explain these two steps?
If we just sum over J. Sorry, I skipped something here.
Mm-hmm.
Which should be
No, it's this one is okay.
this.
Yes, this is AI. Right. And then you plug in it into here. But and then you get
That.
y.
Because we are just summing on J, we still have I.
Mm,
So we just
mhm.
can put this here. It's that.
Okay, but from here to here, how do you get?
Yeah, by duality of mu.
Yes.
This.
Yeah, I think you should write something like this. So mu mu, right? It is what? T. What's the definition? So it's T mu of mu of T mu, right? And T mu, so it's mu, it is mu of, so T mu is like that, AI, HI. So it's sum AI mu of HI. Right? So your T mu is defined like that, so I'm just using this. But then mu of HI, what it is? It is by definition, so it's sum AI, and then, okay, mu of HI, I would like it to be sum AJ, HI, HJ. Then I'm done, right? From here, if I'm going from here to here. Right. So mu of HI it is actually T mu with HI, right? Again, by definition. And which is sum AI hi, well, aj, hj, hi. Yeah, like that. Maybe I need to replace ji, but it doesn't really matter because the form is symmetric. So yes, I got everything that I needed. So it's hi, hj here.
Oh, excuse me for this.
Yes.
Please explain these last.
Yeah, so I'm trying at least to understand why mu mu is this thing. I'm just applying definition for t mu 2 times.
Okay.
So first I say, okay, it's mu mu, right? Yes. So maybe this step is not so definition of t mu, it's rather definition of, so okay, this is t mu. This is how we defined actually form on mu, right? Yes, maybe I even don't need this.
Okay.
Sorry, you actually have, then you just plug in t mu in there, and this is sum a I, aj, hi, aj. Yeah, so just like that. So this is the first step. Then I need this from here to here. Okay, but Ebner says that okay, mu of ki is just you just take
like here we do it with this.
yes,
Just substitute here and rename it.
yeah, because hjki is delta jk, delta ji is just ai, right? So I take but then from here to here, yes, so I have mu of hi is like that, right? And if I plug into this expression, if I plug in these two things, I will get exactly this one. So this are equal. Okay, so therefore, if I take this element and apply to any vector from L lambda mu, I will get this thing. Therefore, if I compute trace, is this thing, or mu mu, times the dimension.
Okay.
And so we got this.
Okay. So it's
And this mu mu is a part of also of this formula, because C mu is mu times mu plus 2 rho, if you remember.
yes.
So this mu mu times m lambda mu that comes out of there is this part of this formula. So it comes from this term in C.
We just have to calculate also the trace
Yes.
in this case.
Yes, and this is the most non-trivial one.
Yeah.
Yes. So let me, okay, thank you very much. Yes. So let me maybe just give you an idea how this one works. So in our notation, what we more used to, it is E alpha F alpha plus F alpha E alpha if I sum over positive roots. So I actually can commute and end up only with this term. So I can take twice of that plus something plus H alpha, sum of alpha in R plus.
Are we not
Maybe minus.
taking F alpha, E alpha?
No, I really would like this one.
Okay.
Why? Because I know how EF acts on representation on vector V. So let me take V lambda, or this is, so the whole idea is the following. I consider now SL2 corresponding SL2 triple corresponding to alpha. So I take my V, I take a V highest weight SL2 alpha weight of highest weight lambda. And from representation theory of SL2, I know how EF actually acts on such thing. This we computed when we, and this was something like k times lambda minus k plus 1 or something. This is the computation we did. So actually now you need to find such vectors in your vectors of this sort in your L lambda mu. So mu is fixed, but v lambda comes from like upstairs each time, right? So you find some singular vector upstairs, and this gives you some vector fk v lambda, and you know how this acts on it by this number, and then another one. But how much? But how? So how you find lambda upstairs? It's just always mu plus I alpha. This.
Yes.
So you go upstairs by adding I alpha. And what's the, how many single vectors of this sort? It's exactly the drop in the dimension. If you take m lambda mu plus I alpha minus m lambda mu plus I plus 1 alpha. So when you go, and if your dimension is here is bigger, then you obtain this much single vectors that at the end will give you this eigenvalue. And so I just need to compute this thing times this and simplify it somehow. It will give you exactly this sum here. Well, and so then you have this also H alpha, and I equals to 0 part in here. That will give you C mu.
Okay.
So this is how all is, everything's related here.